The following is an illustration of the apparatus to explain the effect of a magnetic field on cathode rays. The first component is a closed glass tube. The air inside has been pumped out. So inside the tube there is a vacuum, or has very low air pressure. Can also be called a gas discharge tube. The metal plate at the top is connected to the negative pole of the DC voltage source, called the cathode. The metal plate at the bottom is connected to the positive pole of the DC voltage source, called the anode. Inside the tube there are two circular filters, where in the middle there is a horizontal hole. This filter functions to filter the direction of the cathode rays. Thus, the cathode rays that pass through the inner area of the tube are only cathode rays that have a direction parallel to the x-axis, or horizontal axis. Between the two filters, there is a fluorescent sheet. Fluorescent sheets will emit light when exposed to some type of radiant energy. These are some of the important components of this experiment. After all the circuits have been connected and turned on, light radiates on the fluorescent sheet from left to right, or from the cathode side. This experiment also confirmed that cathode rays did come from the cathode. The luminescence was in the form of a straight line. This is a phenomenon seen during the experiment. We will explain this in more detail later. Now, a magnet is moved towards the system, such that the cathode ray tube is between the two ends of the magnet. On the left side is the magnetic south pole, symbolized as S, short for south. On the right side is the magnetic north pole, symbolized as N, short for north. Note the glow on the fluorescent sheet between the poles of the magnet. The light now curved downwards. Slide the magnet forward again. Light around the magnetic poles curves downward, so the light cannot reach the other end. When the magnet is withdrawn from the system, the glow returns to its original shape. From here, we can see that magnets can deflect the movement of cathode rays. Why is that? Here is a simple view of the apparatus. There are cathodes, anodes, filters, and fluorescent sheets. The cathode emits cathode rays in all directions. The shape of the trajectory is a straight line, in accordance with previous experiments. However, not all directions of these rays can pass through the filter. Only cathode rays have a direction parallel to the horizontal line. When the cathode rays touch the fluorescent sheet will emit light. This is a concept that must be understood first. When there are several cathode rays entering the filter simultaneously, the cathode rays will touch the closest fluorescent sheet. That's why we see light flashing from left to right. Because on that side there is a fluorescent sheet closest to the cathode rays. So, now we know why the shape of the light beam on the fluorescent sheet is a straight line. To explain the next phenomenon, let's assume the filter hole is in the XY plane. So the straight line is also on that surface. Next, a magnet enters the system. We know that around a magnet there is a magnetic field. The direction is from the North Pole to the South Pole. In a two-dimensional Cartesian coordinate system, the direction of the magnetic field is from the negative y-axis to the positive y-axis. If the cathode rays have no charge, they will not be affected by the magnetic field. But in fact, that is not the case. In fact, the cathode rays bend, or deviate from their original direction of movement. This means that cathode rays have a charge. What is the charge of cathode rays? In this case, we must understand Lorentz style. We can watch other videos on this channel related to that concept. In short, if the thumb is the direction of particle movement, and the other four fingers are the direction of the magnetic field, then the direction of the face of the open palm is the direction of the Lorentz force. The direction of the Lorentz force is the direction of deviation of particle movement. This is the right-hand rule for positively charged particles. Since the cathode rays deviate downwards, this means that the cathode rays have a negative charge. From this experiment, we know that cathode rays are influenced by a magnetic field and have a negative charge. We will confirm the charge of the cathode rays in the next cathode ray experiment. Thank you for watching this video in full length. And don't forget to watch the next video.